Okay, the live stream seems to work this time. This is always like tricky. And this one. Okay, so let's get started. It's my great pleasure to introduce Sandra Sibi as our speaker today from EPFL. Sandra is a PhD student at the Security and Privacy Engineering Lab at EPFL. And in her research, she works in the areas of network security, web security, and privacy. And the overarching theme of her research is to understand what we can learn from analyzing metadata in the context of security and privacy. And in particular, she's looking at two use cases, namely improving resistance of networking protocols to traffic analysis and developing automated tracking detection on websites. And today, Sandra brought us a talk about WebGraph. Sandra, the floor is yours. Welcome.
Right. Thanks, Philip, for the intro, and thanks for having me here as well. Hi, everyone. Today, I'm going to talk about this work called WebGraph, which is our work on looking at robustness of ML-based approaches to ad and tracking detection. So in this talk, we can keep it interactive. So feel free to interrupt me while I'm talking and ask questions if you have any. And we can also have questions at the end. So this work is in collaboration with Umar Iqbal, Stephen Engelhardt, Zubair Shafiq, and Carmela Troncoso. So there are a lot of issues with the current online advertising ecosystem. One of the main things is that online trackers, in order to perform behavioral advertising, often collect a lot of information about users' activities on different websites, which is a privacy concern. You also have ads that can be annoying or disrupt the user experience. And sometimes pages with a lot of ads can have performance issues because they might take a long time to load. So all of these issues have led to many internet users making use of these ad and tracker blocking solutions. So you have a lot of extensions such as AdBlock Plus, and even browsers these days already have inbuilt ad and tracker blocking solutions. Now, a lot of these solutions actually rely on manually curated filter lists. So a filter list is basically a list of rules. So as you can see on the slide here, you have, let's say, AdBlock Plus, and AdBlock Plus uses one of these lists called EasyList. And EasyList consists of these list of rules like these. And the idea is that you have rules that are used for blocking network requests or hiding HTML elements, and you pattern match all the resources on a page against these rules and decide which elements to block or hide. And these filter lists are generally maintained by volunteers, and they use like crowdsourced reports of, websites where a particular tracker was detected, and then they add like a new rule to the filter list to make use of this information from the report. So these filter lists have a couple of issues. One of them is that this manual nature of how they are maintained means that they suffer from scalability issues. So it's hard to keep these filter lists updated with the constantly evolving ad and tracker ecosystem. So there's been a lot of research on this, and the prior work has shown that sometimes it can take as much as 3 months to add a new rule to some of these filter lists. It also takes even longer than that to actually remove unused rules from these filter lists. So this means that there is a significant amount of effort that is required to keep them really up to date. And we have also seen from prior work that a large portion, up to 90% of these rules are no longer useful in order to block ads and trackers. The other big issue is to do with robustness. So because these filter lists are using rules that rely on pattern matching, it is quite easy for ads and trackers to actually evade this. And there have been cases where they've used things like domain generation or URL randomization in order to bypass the rules that are there in these filter lists. So keeping this in mind, there's been a lot of effort now towards trying to build automated systems for detecting ads and trackers. So ads and trackers generally make use of different layers of the web stack. So in order to serve ads and trackers, you need like JavaScript, because you might have scripts that have to perform certain activities. Then you have to rely on the network layer, because you might have to send HTTP requests to fetch content from different endpoints. And then you might have to show the ad. So that might make use of the HTML layer in order to visually represent the content. So previous automated detection techniques, they targeted individual layers of the web stack and try to build features that can be used to train a classifier that can identify whether a particular resource is ad or tracking or benign. So prior work has focused either on network layer features, which make use of URL characteristics or HTTP header information, and these features are used to train the classifier. Or they have focused on the JavaScript layer, where they perform either static or dynamic analysis of JavaScript code that runs on the page and uses that to train the classifier. And then we have the next generation of automated detection systems that said that since ads and trackers function across all layers of the web stack, we should be making use of all the information, and this can lead to better accuracy in detecting ads and trackers and better robustness as well. So I'm going to talk about cross-layer approaches in this talk, and I'm going to use AdGraph as an example of a cross-layer approach. So AdGraph was the earliest cross-layer approach, and there have been other systems after AdGraph, but they use the same concept. So we're going to use this as a representative example. So how AdGraph works is that it builds a graph representation of page load events. And here is a toy example to show how that works. So let's say that you have a web page here, this example.com, and this is the code that is related to this page. So on line 2 here, you see that there is a script from tracker1.com, and the contents of the script are shown in lines 4 to 6. And what is happening in the script is basically an image is fetched from tracker2.com, and then it is added to the document. And what AdGraph does is basically converts this into this graph representation that you see at the bottom of the page, where each of the nodes represents a particular element that is happening in the page. And the edges between these elements represent the interactions that are happening on the page. So this is just a toy example, but in reality, you can have web pages and you can have like a lot of nodes and edges such as this that represents all the events that are happening during the page load. So during the page load, you can have events that are just benign. So they might be actually, fetching some style sheets or images to basically render the website's content. But you can also have tracker-related events. And the idea behind these automated detection systems was that tracker-related events have different characteristics than normal benign events. So what AdGraph did was it built a graph representation of this page, and then it extracted a bunch of features and used those features to train a classifier, a random forest in the case of AdGraph. And these features fall into two main categories. So you have content features, which are related to individual nodes in the graph. So they can be things about like the URL or what kind of content it is. And structural features, which are related to interactions between the nodes. So things like how many neighbors does a node have in the graph, how many ancestors, or how clustered it is, and so on. So from the prior works, we saw that these graph-based detectors actually do improve accuracy. So they have good performance in terms of all the classifier metrics. So this means that they are good at maybe addressing the scalability issues of filter lists, because they can identify trackers well, and they can be used to update these lists. But what we were interested in was studying whether they're actually robust to adversarial evasion. And I'm going to talk a little bit about what I mean by adversarial evasion in this context. So let's say that you have example.com, and here example.com is the site visited by the user. So we call that as the first party. And you have a lot of content, for example, an image from image.example.com. So this would also be first party because it is served from example.com. And then you have an ad from tracker.com. So this is a different domain. And so this is a third party. So let's say that you have a classifier. So in this case, AdGraph, and AdGraph has classified all the resources on this page. So it's classified this image as benign, and then this ad as an ad or a tracker. The adversary in this case is actually a third party who's present on the website. And the goal of the adversary is to cause AdGraph to misclassify the resources that they have on the web page and get it misclassified as benign content. So coming back to a question, we actually, when we look at the features of AdGraph, we see that AdGraph relies on content and on structural features. But content features are actually things related to like URL characteristics, for example, and these are pretty easy to manipulate. So we wanted to see how much do these graph-based detection systems actually rely on these content features. So in order to do this, what we did was first we trained an AdGraph classifier, and then we had a test set of about 10,000 sites. And we found the classifier predictions on these sites. And then we applied content mutation on the test data, and then saw how the classifier predictions change if the content mutations are applied. So what I mean by content mutation is I apply domain name randomization and query string randomization. So changing the domain domain name, as well as changing the number and the content of these query strings in the URL. And we experiment with two different collusion models here. So in the first model, which is no collusion, we assume that the adversary, who's a third party, does not have any sort of assistance from the first party, which is the website that is that on which the third party is present. And in the second model, we assume that the third party has limited collusion with the first party. So what we mean by limited collusion is that the first party and the third party don't trust each other to serve their content, but the third party can be a subdomain of the first party. And this is possible nowadays via techniques like CNAME cloaking. And this is a technique that we have seen now that has been rising in prevalence over the last couple of years. And this plot here actually shows the success rate of the adversary for each of the web pages in our data set. And success rate shows the proportion of the resources that an adversary successfully managed to now get the classifier to misclassify. And we see that in the case of no collusion, you have approximately 16% of the resources on each web page now being successfully able to be misclassified as benign content. And out of this, about 21% actually happen to resources that are belonging to ad exchanges. So this potentially has a higher impact because ad exchanges can diffuse user information to more parties in the ecosystem. When we look at collusion with the first party, we actually see a huge jump in the success rate. And we see that having the collusion with the first party is very beneficial. For the third party, the success rate reaches up to 96%, which is a very high success rate against a classifier. And about 32% of these mutations are happening to ad exchanges in this scenario. So we wanted to see why we are having such a high success rate against AdGraph with these simple content mutations. And when we look at the top features that are used by the classifier, we see that they're either related to the length of the URL of the resource, or they're related to whether the URL is a first party or a third party. So this means that the current ML-based approaches, which rely on these content features, are very susceptible to these mutations, which are pretty easy for an adversary to actually implement. In order to see what happens if we remove these content features, if you remove these content features, what we did was we first looked at the performance of AdGraph, and I'm saying accuracy here, but also other metrics such as precision and recall fall in the same range. So we see that when you use everything, the original AdGraph had an accuracy of about 92%. But when you remove content features in order to improve the robustness, you see that the content, this leads to a drop in the accuracy to about 80%, which means that the content features do contribute something meaningful in classifying ads and trackers. And this actually led to our second question, which is, can we actually improve the performance of these systems without using the brittle content features? So one of the things that we observed was that current detection systems, they lack information about how ads and trackers behave. So they have information about what ads and trackers are, which is the content features, but they don't really capture anything related to what ads and trackers do. And when you look at the type of tracking that we are looking at, which is stateful tracking or tracking using identifiers, we see that fundamentally ads and trackers perform two main actions. So ads and trackers need to generate and store identifiers to identify some user. And in order to do this, they need access to storage, for example, cookies. And the second thing is that ads and trackers often share information with a bunch of different entities, for example, using techniques like cookie syncing. So these are the two main behaviors that we feel should be captured by these systems in order to better detect ads and trackers. And they should be captured because it's very hard for ads and trackers to hide what they fundamentally need to do. And so this is why we created our system, which is called WebGraph. And WebGraph basically captures the fundamental tracking behavior by doing two things. It augments the graph structure, which I'll talk about soon, and it introduces a new category of features called flow features. So here's an example of what I mean by the enhanced graph representation. So on the top, we have a code snippet, and at the bottom, we have all the HTTP requests and responses associated with the snippet. So what is happening, there are two main things that are happening in this code. So we have three trackers in this code snippet, and in this top portion of the code, we have tracker 1 that is sending a request for tracker 2. And when it sends a request, it's actually triggering a redirect. And at the end of the request, when the response is sent, a cookie is being set. And in the second part of this code, we have an iframe from tracker 2. And this, this iframe is sending a request for tracker 3. And it's taking the cookie values that it has and sending the cookie values in the URL. Now, if you look at AdGraph representation of this code snippet, and it basically looks like this, and you have these two sort of disjoint graphs representing the two main events that are happening that I just described now. But if you look at the enhancements that we have made, we actually see that these two events are not completely disjoint, because there are a lot of cookie sharing events that are happening between these trackers, which are not being captured by AdGraph. So the enhancements that we make in order to capture these events is, first we add a storage layer, which is not present in the current ad and tracker based systems. So we add all the events that are happening to cookies or local storage. as nodes in the graph. And then the edges represent whether the storage elements are being set or accessed. Yes, somebody has a question.
Yeah, so I have one quick question. When you talk about the read cookie storage, is it about the index DB or the cache?
This is about all the document.cookie get accesses using the doc. Yeah, and also for the local storage API.
Okay, sounds good. Sounds good.
Anything else? Okay. Yeah, and the second thing that we're looking at is actually redirects. We found that in AdGraph, they're not actually capturing the redirects that occur, and redirects are often used in tracking activities such as cookie syncing. So we capture redirects as well in our enhanced representation. And finally, we introduce a new type of information, new type of edge called shared information edges. So this means that if two nodes actually access the same storage node, there is a shared information edge between them. So for example, let's say that a node sets a cookie and later on this cookie value is read by another node. There will be an edge between the two nodes that are interacting with the same cookie. Or for example, if the cookie value is set by a node and then the value of this cookie is shared as a URL parameter to another endpoint, there will be a shared information edge. So in order to implement these, we actually use a system called OpenWPM that allows us to run crawls with an instrumented version of Firefox. We put our own instrumentation in order to capture some of these events that we require in order to build the graph. And then we use the OpenWPM output, which is all the network requests and the JavaScript activity that takes place during a page load in order to build this graph representation. And then finally, for WebGraph, for the features that we use, we get rid of the content features, we keep the structural features, and then we introduce a new category called flow features. And the flow features are related to the enhancements that I just spoke about. So we use things like how many times a cookie is being set, or graph properties that are related to the shared information edges in order to build these flow features. After doing this, we look at the performance and we see that using the new flow features actually raises the performance of WebGraph to about 87%. So this is a big jump from the loss of the content features. We don't approach the original performance of AdGraph because I guess the content features still do add some information that we're still missing. But this could potentially be improved by adding more information flows that are related to ads and tracking. And more importantly, when we look at the robustness of WebGraph and we perform the same content mutation attack against WebGraph, we see that the success rate of the adversary drops from 96% to 8% against WebGraph. So this means that dropping the content features really helps in the robustness. And with these flow features, we actually get an improvement in the accuracy. We wanted to know next whether WebGraph is robust to more sophisticated evasion. So right now we see that there are these content mutations, but we can imagine that in the future, ads and trackers will perform more sophisticated techniques that actually target the structural and the flow features that are used by WebGraph. So here's a toy example to explain what kind of mutations an adversary could do. So let's say that you have a web page here, example.com, which contains content from different parties. So you have the first party, which is here in blue, and then you have the adversary here in pink, and then content from other third parties as well. And then we have WebGraph, and the WebGraph has originally classified each of the resources on this page as either benign or as ad or tracker. So what the adversary would try to do is, so the adversary owns the pink nodes on the page. So the adversary can perform a mutation by adding a child node to itself. So how does it do this? It does this by just sending out an HTTP request, and that leads to generating a child node and an edge in the graph. And this actually causes a change. It can trigger a change in the classifications of WebGraph. And this is because when you add child nodes, the structural properties of the nodes change. So for example, the number of children of this node now increases from 0 to 1 and so on. So by changing the structural properties, you can trigger a misclassification by WebGraph. And the same way, the adversary can do another mutation where it tries to add a child node in another part of the graph, like to another one of the resources that it owns. Now, what happens is that some of these classification switches can be desired from the adversary's point of view, and some of them can be undesired. So the problem with these structural mutations is that they don't just affect the nodes that are owned by the adversary, they would affect the structural properties of every other node on the graph. That means that it is possible for other nodes in the graph to now undergo a misclassification. So if the adversary gets their own resources as now classified as benign, that is good for them. So it's desired from their point of view. They might not care about certain other mutations. For example, if this third party now has a misclassification, the adversary might not care what happens to another third party's resources. Sometimes it can trigger a mutation in the first party's resources, and the adversary, depending on the sort of end goal of the adversary, this may or may not be desired, because sometimes if the first party's resources now get misclassified, then it can lead to website breakage. So functional content might no longer work, and this might prevent a user from actually using the web page. So what the adversary does is it calculates the desired and the undesired classifications, and it picks the mutation with the best trade-off between the desired and the undesired classification. And then it does the same thing. So you can go, this is just one round of the mutation, but you can imagine that the adversary goes through multiple rounds where it tries to add different number of nodes, and it sees how this impacts the classifications on all of the nodes on the graph. So now we perform resource addition, which is what I showed here, but in our paper, we actually perform other kinds of attacks as well, such as rerouting and obfuscation, which all target the structural and the flow properties of the adversary. So in rerouting, we imagine that redirects are now sent as individual requests, and that completely breaks up the redirect chain patterns. In obfuscation, we see that cookie values could potentially be in URLs could potentially be obfuscated using some encryption that WebGraph is not aware of. So we did this. So this is the result for how WebGraph performs against these misclassifications on a set of 100 pages. So on the x-axis, you have the success rate, which is the same as before. It shows the proportion of web pages, the proportion of resources that the adversary could now successfully get misclassified. And now we have this new thing called collateral damage. So this looks at what are the undesired switches that the adversary has from their point of view. And ideally, you want to be in the sort of bottom right of this plot, where you have high success rate but low collateral damage. And we see that this is not necessarily the case. So you might either have low success rates, or you might have a decent success rate but then high collateral damage. But the most important thing that I want to highlight here is that these kind of attacks are actually difficult for an adversary to implement in comparison to the content mutation attacks, because they target flow features. if you want to do this kind of changing of the information sharing patterns, that actually means that you need to change how you're sharing this information with a different endpoint. And in reality, this means you need to coordinate with all the partners that you're sharing information with and actually implement these changes on both sides of this communication. Another thing is that if you are trying to change the patterns by sending out more HTTP requests and so on, this is actually also a higher cost for the adversary. So these kind of mutations would only work if the adversary is able to easily coordinate with the other endpoints with which they share their information. And also they're okay with tolerating the side effects on other nodes in the graph. So here are some of the things that are, let's say, limitations of WebGraph right now. So, so far I've spoken about WebGraph, and we are looking mainly at stateful tracking or tracking using identifiers. But there are other forms of tracking, such as browser fingerprinting, for example, that we are not currently looking at with WebGraph. At the same time, it is possibly easy to enhance WebGraph by also capturing like popular JavaScript APIs that are used in these browser fingerprinting methods and develop a system to also detect stateless tracking. The second thing is about the information flows. So in our version of WebGraph, we have captured like common information flows and kind of approximated what kind of flows are being used by ads and trackers. If you want to actually cover every single information flow, you might have to do like a taint analysis, but this can lead to high overheads, which is why we have not chosen to do this. So there are ways in which we could potentially enhance WebGraph. The second thing is about the robustness experiments. So we have chosen like a greedy algorithm here in order to find the best mutation. So in every round of the algorithm, the adversary just picks what is the best trade-off between the desired and the undesired classification, but this might not necessarily be the best way of getting the ideal mutation for minimum collateral damage and maximum success. So looking at more sophisticated mutation algorithm could be another avenue for improvement. And finally, we originally envisioned WebGraph as an offline deployment tool. So we envisioned that a WebGraph could be used in order to help filterless maintainers. So you would run this on the whole web page and detect all the trackers, and that can be used to enhance filterless. But we can also envision WebGraph being deployed somehow as an online tool that does tracker blocking on the fly. So in summary, what we actually find in this work is that current graph-based tracker detection systems are heavily reliant on these content features, and we should ideally move away from using these brittle content features in these systems and focus more on capturing fundamental behaviors of ads and trackers, because they are difficult for ads and trackers to hide. And with WebGraph, we raise the bar for ads and trackers attempting evasion, because these structural mutations are actually difficult to implement in practice. So we have our paper link here, and we are hoping to release the code soon, possibly in a month after some cleanup. And yeah, that's it. I'm happy to take questions.
Cool. Thanks a lot for the very nice talk, Sandra. I'm stopping the recording and the live stream, and then we can go over to Q&A.